Welcome back. We've had a little bit of a break from videos, but we're getting into radioactivity now, and this lesson is going to be on radioactive half-life. First, a little hint. This is something that sometimes people trip up on tests and quizzes. They don't look at every single page. Check every single page in the evaluation to make sure you don't miss anything. So moving on. Today we did radioactive half-life. We did radioactive decay, and then I introduced you to half-life. This is a visual of the same thing, it's just a shortened version. So half-life, the basic idea behind half-life is after one half-life, half the sample will be gone. So the original sample, say in this case, was 16 grams. We'll call each of these spheres 1 gram. So if it had a half-life of 1 year, then after 1 year, 8 of them are gone. So 8 are remaining. So half the original sample is remaining. After another year, half of that amount of sample is remaining. So it was 16 here, it becomes 8, and after 2 years, it'll be 4. 4. Half of the 8. So each half-life period eliminates half of whatever's there. That's the concept behind a half-life. So, by the way, there is a handout that's worth grabbing at this point. It gives you a little bit of an introduction to logarithms. I'm going to talk about them as well, and it introduces you to some of the stuff in this. So it's worth downloading it right now. You can go along with what's happening here. You can try and work your own way through the handout first.
Ms. Johnson, would you please contact us out?
So, next slide. This is a visual, a graph of half-life. What we're doing here is we're plotting percent of the sample versus the time in years. So if we were to look at this, pause the video in a second, pause when I say, and tell me what the length of one half-life of this substance actually is. So pause it now and see if you can determine what a half-life is. Okay, so hopefully you realize that after one half-life, it would be down to 50%. So you can trace that over to this point, which corresponds to about 2.7 years, because the scale is in years on the bottom. And if we wanted to go further, after 2 half-lives, it would be down to 25%, so that would be here. At 25%, we are right around here, which is, close enough to 5.4 years. And if we went even further, we could go down to 12.5%. 12.5% would be around there, and that would give us about, what is that, 8.1 years. So 2.7 is probably close enough, because this is a gap of 2.7, this is a gap of 2.7. Of course, I'm making assumptions when I do this. On the graph, it's not that precise. We can do calculations, however. And here's one to try. So pause the video now and see if you can figure out the answer to this question. So, sample of lead. What is the half-life? So we're looking for half-life. And it's going to be probably in hours, because our times are in hours. So I'm going to say hours, and if I'm wrong, we'll change it then. So what we have, information that we have. We don't have to draw a diagram for this. You can if you want. It's easy enough. It'll look a lot like this diagram back here. So what we're doing is we're starting. So the initial mass, 200 grams. Final mass is 25 grams. So we have to figure out how many half-lives it took to do this, and what the total length of time. So the total time elapsed is equal to, well, we started at 8 o'clock one morning and ended at 2 o'clock the next day. So that's 24 hours to get to 8 o'clock the next morning, and then another 6 hours. So the total time is 30 hours. And we want to figure out how many half-lives that is, because we're trying to find the half-life. Now, logically, hopefully you were able to realize that to get to 25, we can start with 200. One half-life would take us down to 100, half of the original. Another half-life would take us down to 50. And another half-life would take us down to 25. So that's 1, 2, 3 half-lives. So this is equal to 3 half-lives. And since the half-life is constant, that means it's just 30 divided by 3. So the half-life equals 10 hours. because 3 sets of 10 hours would happen in 30 hours. So the half-life of this sample is 10 hours. Now, I've lost my timer. 5 minutes. So we'll keep going. Let's see how far we get. I may have to do the examples on in another video. Next page. So we have to do some math to really be able to handle half-lives properly, radioactive half-life, because there are some things that are a little bit awkward. So first thing, exponents, and this will be in your handout, so I'm just going to go through it very quickly. 2 to the power of 5, 2 times 2 times 2 times 2 times 2, which equals 32. That's what 2 to the power of 5 means. 0.5 to the power of 3, well, 0.5 times 0.5 is 0.25, so that's to the power of 2, times 0.5 is 0.125, 0.125. Or, another way of putting this is 1/2 times 1/2 times 1/2, which is equal to 1/8. 2 to the power of 3 times 2 to the power of 2, well, 2 to the power of 3 would be 8, 2 to the power of 2 would be 4, and that equals 32, which, amazingly enough, equals 2 to the power of 3 plus 2, which is what we did up above. Okay, so I'm just showing you some of the tricks. 10 to the power of 3, another thing that we should look at. 10 to the power of 3 is 1,000. 10 times 10 times 10. Now the next thing to look at is 10 to the power of what equals 10,000? What exponent do you have to put 10 to get 10,000? Well, that would be 1,000 times 10, so it's actually 10 to the power of 4. Another one you can work out, and you can pause the video and try this, 0.5 to what power gives you 0.015625. So pause the video, see if you can get that answer right now. All right, we can approximate. 1/8 is about 0.125. If we divide that by 2, we're going to get something around 0.06. If we divide that by 2, we'll get something around 0.03. And then divide that by 2, we get something around 1.015.
Mr. Briggs, Mr. Clifton to the front of the school, please. Mr. Steva, Mrs. Briggs, Mr. Clifton to the front of the school, please.
So this was 3. So this would be 4, 5, and 6. So this is going to be 6, 0.5 to the power of 6. These are all things that you can look at. If you're struggling with any of these, go back, have a look through them, maybe look at something in the Khan Academy on exponents. Now logarithms take exponents and go backwards. So basically those last 2 examples I gave you are actually examples of doing a logarithm, just not explicitly said that way. So 10 to the power of what equals 10,000? Well, the answer to that is 4. Another way of saying the exact same thing is this. The logarithm base 10 of 10,000 equals 4. So what we're saying here is, what power do we have to take 10 to get 10,000? And the answer is 4. So this would tell you that 10 to the power of 4 equals 10,000. Again, we just worked this one out. It's 6. So the way we would say this with logarithms is the logarithm with a base of 0.5 of 0.015625 equals 6. So taking it a little further, punch these 2 numbers into your calculator just for interest's sake. 10 to the power of 2.5, you should get something around 316. That means that the logarithm, base 10 of 316 equals 2.5. Try that on your calculator. You should have a button that says something like this. Don't press the button that says this. That's something you might get later on in calculus. You don't need it right now. All right, so log. Now, when you use the log button, it assumes you mean this. And that's all we'll need to do in this unit. All right. Let's check my time before I take this a step further. Coming up to 10 minutes. I think I'm going to stop here and we'll continue in another video so you can take a break. So make sure at this point, review your exponents and take a look at what I've just told you about logarithms. practice making some logarithm exponent relationships on your calculator. See you in a bit.